Testing mic 1 2 3. Testing 1 2 3. Can everyone hear me?
Yes, yes.
Okay, thank you.
Hello everyone, Assalamu alaikum.
Hello.
Waalaikumsalam.
Hello.
Hello, anybody listening me?
Yes, we can hear you.
Yes, we can hear you.
Hi, Mr. Javid, we can hear you.
Can you hear me, Nurul Huda?
Yes, Prof.
Okay. So I like to test my screen sharing quickly. Can I do that?
Yes, Prof.
Okay, hold on a second. One second. I'm going to make it full screen. 1 second. Then I'll come back.
Okay.
Oh, can you see my full screen?
Yes.
Changing?
Yes. Yes,
Okay.
changing. Yeah.
Let me go back, and I would give the screen back to you. And I can, when you are finished introducing, I can come back. Okay.
Okay. Li Xiaojian, Li
Yes.
Xiaojian, you okay?
Yes. All good.
Okay. So we pass the mic to you. Okay, good.
Okay.
We have a few minutes left, 2 minutes left.
Assalamualaikum.
Waalaikumsalam.
Ladies and gentlemen, the webinar will begin shortly. Please remain on the line. You are also be reminded that please do not start the recording by yourself. The organizer will do the recording. Thank you. Honorable Dr. Harun Rashid, Counselor of IEEE PAS Student Branch Chapter, Counselors of IEEE UKM Student Branch, Associate Professor IR Dr. Nohana binti Asad, and Dr. Iskandar bin Yahya, distinguished guests, ladies and gentlemen. First of all, I would like to welcome you all to this webinar. My name is Li Xiaoxian. I'm the moderator for today's webinar. Before we start, let me explain how you can talk to us during the webinar. If you have any questions during the presentation, just write them in the meeting chat. We will have a Q&A session at the end of the presentation to answer your questions. Alternatively, you are also allowed to raise your hand during the Q&A session. You will also be reminded to not stop the recording because the organizer will arrange the recording. In conjunction with the theme of the 4th IEEE PAS Day, Clean Energy Revolution, we would like to have a presentation about the role of the smart grid in facilitating the integration of renewables. Before the presentation begins, I would like to introduce the presenter. He is Professor Saifur Rahman. Professor Saifur Rahman is the founding director of the Advanced Research Institute at Virginia Tech, USA, where he is the Joseph R. Rowling Professor of Electrical and Computer Engineering. He also directs the Center for Energy and the Global Environment. He is a Life Fellow of the IEEE and an IEEE Millennium Medal winner. He was the president of the IEEE Power and Energy Society PAS for 2018 and 2019. He was the founding editor-in-chief of the IEEE Electrification magazine and the IEEE Transactions on Sustainable Energy. He has served as the chair of the U.S. National Science Foundation Advisory Committee for International Science and Engineering. He has published over 150 journal papers and has made over 600 conference and invited presentations.
Thank you, Shaoshian. Let me share my screen. Can you see my full screen, Shaoshian?
Yes, we can see.
Okay. Assalamu alaikum. Good evening. Happy Ramadan to everybody in the audience. I'm happy to come before you this morning, my time, evening, your time, to share my experience about smart grid and renewables integration. If you want to know more about me, I have my website at the bottom of the screen, srahman.org. It has more information about my research activities, other lectures, and so on and so forth. So with that, let's move on. When we talk about smart grid, we have to define broadly what smart grid means and what this is going to give us. Smart grid is a concept with the many elements where monitoring and control of each element in the chain of generation, transmission, distribution, and end use allow us to deliver electricity in the most efficient way. Many keywords here. First is to monitor and control. Before smart grid, we did monitor voltage, frequency, power flow, current rating, all of that. We never control them. Smart grid gives us technology to control what we want to control. That's one. And it spans from generation to transmission to distribution to end use, that your home and your office. And the objective is to make electricity delivered in the most efficient possible way. That's smart grid objective. As I said, this is a concept, not something you get done. It's never done. You can always keep on improving as we go forward. So let's talk about the word grid. Grid means network. This is the electric power grid, which is network of high voltage lines connecting long distances. If you want to restrict your smart grid to the electric power grid alone, nothing much else can be done, because this grid is already very smart because of technologies like fax devices, PMU, and so on. So this is not the issue. Issue is, as I said, transmission, distribution, end use. We will focus on those as we go forward. So what is then is the motivation behind this smart grid? We would like to make the grid smarter, safer, reliable, and more cost effective. That's important because we are not saying smart grid is cheap. It's not cheap, it's very expensive, but it is cost effective. I'll tell you why. So how we get that objective met using advanced sensors, communication technologies, and distributed computing. We'll give you examples as we go forward. So keep the word in mind. It is cost effectiveness, not low cost, we are focusing on. To explain the difference between a smart grid and not so smart grid, I use this telephone analogy. On the left-hand side, I have the old rotary dial telephone, which has been there for 60, 70, 80 years before smartphones came to the picture. That normal phone costs about $15 US. Most of you in the audience have not seen it, I'm sure, but that's how we made phone calls. Even today, some offices have these phones. If you want to make a phone call only, that phone is good enough. The black phone, rotary dial phone is good enough. In fact, the voice quality on this phone is better than voice quality on a smartphone. That's why we say sometimes, please call me on the landline phone. Landline phone is this phone, landline phone, connected. Right-hand side is a smartphone, happens to be an iPhone. This iPhone 12 costs more like $1,500. $15, make a phone call, $1,500 to make a phone call. If you want to make a phone call only, why should you spend 100 times more money? You don't want to. You spend that much money because the iPhone on the right-hand side allows audio phone calls, of course. You can do Facebook, you can do WhatsApp, you can do a camera, you can do a lot of apps, many things can be done. You can do a spreadsheet, PowerPoint, you can do email, all of those things are done. The point is, if you are given the opportunity to do more things with one object, here the smartphone, you are willing to spend the money. This is the point. Smart grid will make life easier for you. It'll do more things for you. One grid network can do many things. I'll show you in a few minutes. That is why we spend the money. So keep in mind, it is cost effective, but it is not cheap. That's the difference between a normal grid and a smart grid. Okay. Then the question is, where does the smart grid start and where does it end? The smart grid starts at a power station, then goes through transmission network, distribution network, homes and businesses, buildings, and finally you're on your home and your end user appliance, refrigerator, air conditioner, television, computers, lights, fans, all of those. I say, to make it simple, the smart grid starts at the generator and ends at the refrigerator. That's the span of smart grid. How is the grid changing and has changed in the last 10 years or less? The top third of the screen here shows you before smart grid. Standard network, you can see here. Power plant, which produces electricity. Step-up transformer, high voltage transmission line, neighborhood step-down transformer, electricity poles to buildings and homes, and that's it. That's the normal grid, and most all countries have this today. Then we begin to deploy smart grid technologies to this normal grid. Now, what is new? If you look at the bottom half of my picture, you see solar panels, you see battery, you see electric vehicle, the green car at the bottom, you see wind turbines, you see buildings connected with blue dotted line. The blue dotted line represents telecommunication line. Of course, you have power lines connecting these, but in addition to the power lines, you have telecom lines. That's the new thing. That makes the grid smarter. That means smart grid must have full telecommunication connectivity between the source and the load. This is new, fine. So what we are saying, we have to merge the power flow with information flow using integrated communications network. This is your power infrastructure. We just saw that, right? On the upper left-hand side, central generating station, step-up transformer, power line, coming to your neighborhood, receiving station, distribution substation, that brings power to the lower left-hand side, homes, buildings, which may have rooftop solar, may have batteries. Straight down on this screen here at the bottom, industrial customers who may have cogeneration. That means these customers, industry, those who need steam, will burn fuel to produce steam, and that steam, before used as steam itself, can be used in a steam turbine to produce electricity. That is called cogeneration. On the lower right-hand side, we have commercial building. Some may have flywheels. I know here in Northern Virginia, where I live, the AOL data center has flywheel as a backup power. This is a customer-owned generation to the lower right side. And that's it, commercial building. So this is the existing electric power infrastructure. What is new? New is we are now adding an information infrastructure on the electric power infrastructure. That's the red lines connecting all these loads and sources. You'll also notice this set of red lines have arrows left to right, top to bottom. What does it mean? That means two-way communication. So not only power company can read my meter, I can ping the power company's dashboard to find out what is the price of electricity at this very moment. This is the example of two-way communication. Good. That's the discussion on a smart grid. Now let's focus on renewable energy or solar-based or green energy, as we have said for your seminar event today, green energy. We have wind turbines, rooftop solar. What is new also is electric vehicles, and Malaysia has it. We have EVs now all over the world. So electric vehicles are run on electricity. They need a lot of power to run them. So question then is, where is the power coming from? Those are the challenges we have to deal with. Fine. Now, let's talk about the variations and properties of wind power in many countries. I'll show you some examples from US. This is data from northwestern US, Washington State and surrounding areas. The company is called BPA, upper left-hand side, the Bonneville Power Administration. Here I show you a typical day in January, winter time. In the US, because of heating load, we have two peaks in winter. Morning peak about 7, 8 a.m., evening peak about 6, 7 p.m. That's normal. That's the typical day in January, load shape at this power company's service area. Below that, you have the red line, which represents the wind power output, a typical day in January. They don't match very well, because when your morning peak is 9,000 megawatts, the wind power about half the peak, less than half. Then the wind peaks at about 2 p.m. when the demand is low. Then the wind output comes down. By the time the second peak happens, wind output is half the peak output. That means, in addition to short-term variability, the wind output does not match the demand for power. That's a challenge. How we deal with it, we'll come back, discuss furthermore. That is month of January, winter. Let's look at spring, April. Same data set, blue means power demand, red means wind power, no match at all. In the morning time, morning peak, 8 o'clock or so, wind is okay, half, 60%, 70%. By the time the second peak happens, wind output is about 25% or 20% of the peak. No good match. Let's look at summer. Similar issue. You are noticing here from season to season, the load shape is changing. Also, the wind output is changing, interesting enough. This is, we realize that the wind output is the same over the year. It changes from season to season, in the morning, afternoon, evening, and so on. Here is a summer load because of air conditioning. We have a broad peak period, 10 a.m. to or 11 a.m. to about 8 p.m. And the wind output is totally off. In fact, the wind output was lowest at 5 p.m. when the peak was the highest. Load was the highest, wind output is the lowest. If you want to depend on wind power, in this case, to supply your load, you'll be in bad shape. So we have to talk about what else can we do. That's the summertime. Let's look at one more. October, which is fall or autumn season. Same thing, the blue line is the electrical demand. Again, because of the heating load coming back in October, heating season starts, I got back my two dual peak power demand curve. Morning peak about 7, 8 o'clock, evening peak about 7 p.m. Here in the month of October, my wind output is better in terms of shape matching. I can see the wind output was fairly high all day till about 4 o'clock or so I could catch the morning peak. Then by the time the evening peak happened, my wind output is less than half or 30% of my peak. Again, point is they don't match very well. Good. There is wind. Let's look at solar. This is my building at Virginia Tech where I work. This is a clear sunny day, rooftop solar. I put the solar project on the rooftop of this building to see how the solar output shape match or does not match with the power demand. So let's look at one more example. This is similar sunny day, but winter time. Rooftop solar is covered with snow. If it is sunny, like this picture, and rooftop is solar panel is covered with snow, there's no output. Even though it's sunny, no output. Those are the challenges we have to deal with. So let me show you some examples. This is a clear sunny week data for my rooftop solar, and the size of the array was 6.5 kilowatts. I'm getting pretty good, 5.5 kilowatt most of the days. That means 80-90% of the rated output. Clear week, clear week. Let's look at a week which is not so clear, partly sunny, partly cloudy. Output is about half the normal. So my point is, if I have to depend on my rooftop solar to run my building, some days, some weeks, I'll have problems, like you see here. So that's the weekly. Let's look at daily data. This is one day fairly sunny, some clouds moving in and out. That's why you see those spikes. Cloud came in, power went down, not zero. Cloud moved away, power came back. This happens. So question then is, if this is something you have to deal with, how would you manage? You can put batteries, but batteries are expensive. What I'm going to tell you, smart grid can give you some help. In what ways? Smart grid is able to control building load for short duration using no batteries. We can dim some lights. We can change the setting on the thermostat. We can turn off some fans for a short period of time. We can use some plug load controller or smart switches to control lights, fans, and other loads for short periods of time. You can imagine looking at this picture, if my supply is doing this and my demand can be adjusted, meaning when the supply is limited, I can drop my load for a few minutes or at a time. That's the smart grid application to integrate renewables in the grid. Good. This is a fairly sunny day with some cloud moving in. Not so sunny day, similar issues, a lot of spikes because sun is moving in and out, and we have to be worried about how to deal with this. Again, these are your challenges. This is your changing load. How to match it will be our challenge, and a smart grid can help us to achieve this goal. So what are the storage options we have to deal with the variations? Of course, battery we talked about. These are large batteries used to back up wind output or provide supply backup for city applications and so on. This is available, pretty expensive. Lower left-hand side, example of a pumped storage hydro project, which is used to pump water from a lower elevation reservoir to a higher elevation reservoir so that you can turn the water back down during daytime peak load hours, so produce electricity when the demand is high. So this is how you control the supply and demand. So at nighttime, demand is low, you turn the machine on, use it as a motor, pump the water to the upper reservoir. Daytime, demand is high, turn the power flow back from top to bottom. Those same machine which worked as a motor will work as a generator now and produce electricity. The switching time between supply and demand is about 3-4 hours. This is the pumped storage. On the lower right-hand side, I have compressed air storage, which is an example of compressing air from the atmosphere, throw it or push it into an underground cavern, like a salt cavern or something of that sort, a big hole in the ground, and store the compressed air there. So you can see the picture, the blue diagram in the middle. I got a motor which runs a compressor that pushes compressed air into the ground in the salt cavern. That's during off-peak hours. You also may know that a gas turbine requires compressed air to run. What happens typically when you start the gas turbine, first few minutes, you'll compress air during peak hours and then do the combustion in the gas turbine itself. That means during peak hours, you're using more electricity to compress the air to begin with. What is happening here? Because I have now ready supply of compressed air in the salt cavern, I don't need to use electricity during peak hours to run the compressor. That saves electricity during peak hours and run the gas turbine. This is another example of storage, compressed air energy storage. The cycle time maybe few minutes, an hour or so, not few seconds for a battery. Battery few seconds, pump storage few hours, compressed air maybe 30 minutes or so. Time difference between supply and demand. Supply means compressed air supply, demand means run the compressor to compress the air. Okay, so this is the difference now. New paradigm for the power system. Historically, we said demand-driven supply. Demand was unknown, so we can forecast demand, and based on the expected demand, we produce electricity or build new power stations, buy from neighbors. Those are the supply adjustments based on demand changing. Demand was the independent variable, supply was the dependent variable. I say here in red letters, supply responds to demand. Supply changes as demand changes. Now things have reversed. I call it supply-driven demand. Why supply-driven demand? Because now my supply is unsure. Wind changing, solar changing, hydro changing. If supply is unsure, what can you do? You can use some battery, okay, but bigger supply support can come from adjustable demand. We just saw the demand curve for the building. So how do I control the demand? It's coming to that. Point is, just think about this. New reality, supply-driven demand. Demand has to change based on supply changes. I call that smart grid ecosystem, okay? Here it is. Start at the bottom, the yellow circle, smart building. If you read the bottom paragraph on the right-hand side, what is a smart building? It has intelligent building automation systems, smart devices, productive users, and grid integration. Okay, what does it mean? Intelligent building automation systems. In this building, smart building, I have sensors, controllers. It'll sense the sunlight is decreasing. Based on that information, it will change the demand by dimming some lights, changing thermostat setting for air conditioners, turning some fan off for a short time, changing some plug load schedule. That's the smart building automation system. That makes the building sensitive to changing supply. If that is how you design the building, you will not have to depend so much on storage. Some storage, okay, I don't know a whole lot. That's smart building. Then smart campus, like UKM campus, your campus, has a lot of buildings. If you can make those buildings smart, as I defined below, you have a smart campus. Then you can deal with variable supply more easily. Next smart city would be KL, right? Many campuses in KL, and if those are smart campuses, you can have a smart city. Finally, smart grid. Like Tenaga Nasional Berhad, TNB is a network. So if they have many smart cities in the country from KL to Johor Bahru, you can have a smart grid network. That's the hierarchy. That's what I mean by smart grid ecosystem. That's it, my friends. Thank you very much. I've given you my email address, my website. I'm also on Facebook, LinkedIn, Twitter, and YouTube. You can find me there as well. Also, my website has more information about my research in terms of these presentations on different topics. Feel free to use them. And I will have time now to take some questions. If you have other questions later on, you can email me at this address. I'll be happy to answer. So Xiaosheng, with this, let me stop screen sharing. You can take over.
Okay, thank you, Professor. Thank you for the interesting presentation. All right, ladies and gentlemen, now we have come to the Q&A session. You may write your questions in the meeting chat or raise your hand. Yes, Tan Chishan. Mr. Tan.
Hello everyone. I have a question here. I would like to ask, where do you see the smart grid technology in 10 years?
Okay, good question. Smart grid has to be deployed part by part. Cannot do the whole network, cannot be smart grid one night, cannot be possible. So what I have done, I've not talked about this today. I would see, I think there will be microgrids inside a network. A city could have 3-4 microgrids, which are all interconnected, and that each microgrid will be easier to handle in terms of deploying technology, managing testing, and all that. So, answer your question, I would expect next 5 to 10 years, we'll have many microgrids inside a net power grid, which would be the building blocks of the smart grid. And over time, that will spread. So right now, one power company may have 2 or 3 microgrids. They will have 1,000 microgrids 10 years from now. Each microgrid will have their own control protocol, solar, wind, storage, all that. It's much easier to handle as opposed to managing the whole country as one smart grid. So wait at least 5 years, maybe 10, before you see these more widely applied. Thank you.
Okay, thank you, Mr. Tan. Is there any other questions? You may feel free to post it in the meeting chat or raise up your hand.
Hello.
Yes.
Hi. Yes, good evening.
Good evening, doctor. I want to ask that is it any required skill to become
I hear noise. You can hear the question.
Sorry, Mr. Tan. Can you
okay,
please repeat your question?
Okay, so after listening this, so may I know, is it any skill or required skill to become a smart grid engineer or not? Or other skill?
Okay. Smart grid encompasses electric power, telecommunication, computing, and signal processing. So if you're an undergrad at UKM or anywhere else, I would recommend, if you want to work as a smart grid engineer down the road, take some courses in telecommunications, power, signal processing, at least those 3, so that you have a broader understanding of the building blocks of the smart grid. You can deal with those problems more effectively. Xiaoxing, I see a question in the chat box.
Yes, sure.
Marisa Ong, and let me read that question. Does smart grid system smart enough to help consumers to manage the electricity bill? If yes, how? Very good question that is happening today in parts of US and other countries, some other countries. In many countries, the price of electricity changes from hour to hour in the day, hour to hour during the day. So summertime, 3 to 6 p.m., lot of air conditioning load, demand is high, price is high. So customers don't always pay attention to that. So they end up paying more for the afternoon peak hour. What smart grid can do, smart grid, or if you have a smart in your home, have a smart meter, which I have, it can send you signal on your smartphone. Today from 3 to 6 p.m., power will be twice as expensive. You get that information. How can smart grid help? You can design a home automation system, which is available. I can talk about more later on, whereby you send a signal to the home automation dashboard telling the power cost is high from 3 to 5 p.m. Please do not run heavy duty equipment during that time. Do not heat the water. Do not run the electric clothes dryer, for example. Do not use the AC as much. Do not bake your cake at that time. So you can avoid using high price electricity. You can do those things after 6 o'clock when the price goes down. You can program this in the smart meter in your home automation system and achieve this goal as you go forward. Thank you.
All right, thank you, Miss Larissa. Mr. Selwyn Hao, is there any questions?
Yes, good evening, everyone. I have a question. So will smart grid engineers be automated or replaced by robot in the future? That's my question.
Oh, you need human beings. I'll tell you why. Robots has to be programmed, and you can use robots to make cars. You can use robot to run electric power system. It's too dangerous. So I don't think because of robotics large scale application, power engineers will lose their jobs. They will not, because you have to make a lot of decisions and make changes as environment changes around you. Suppose it's a very hot summer day and the price of electricity is high because it's very, very, very high in demand. So rain comes in, I've seen that. Rain comes in, demand drops. But then you can allow people to bake their cake if it rains. A robot cannot figure it out. So my point is you have to be a human being to take into account changes to make sure you are more flexible. You can say, if I can program the robot, if it rains, do this. You can do that. But then we have to make sure robot is not making a mistake. Then you can say, okay, I can put a second robot to check the first robot. So then you got more robots than engineers you had to begin with. It's not any cheaper. So let me see if there are two more questions. One is from Ongwe Lee. Are there any security issues triggered by the implement of smart grid system? Yes, there is security issues. As you can see, I'm talking about more and more automation. If you do more and more automation, you expose yourself to hacking and other people trying to take over. So what is an issue here is cybersecurity. A lot of work is going on today to ensure a network is protected against unauthorized access. So that is going on. Second is, can you comment on the cost of setting up smart building infrastructure, especially in campus? It depends on what you want to do. I have done that in a building at Virginia Tech, and it cost us several $1,000s. And they saved electricity because of the control they can use from the smart building controllers. And they got their money back in 2 years or so. That means they saved enough money with lower electric bill because of the smart building application. And because of low electric bill, they saved money. And that money was enough to pay back the loan that was used to run the system in 2 years or so. So that's what I can suggest. If you want to know more, there is a company that I know about here in Virginia that you can go to their website. I just put that on the chat box, in the chat box. BEMcontrols.com. They have more data, more information about this smart building deployment. BEMcontrols.com. Thank you.
Prof, there's Mr. Ho Chang-kit. Would you please ask your questions?
Yeah, good evening, Prof. I would like to ask, it is said that a normal consumer is expected to be able to turn or to both careful customer and prosumer in a smart grid system. Do you agree with this statement?
Yes, generally speaking, yes. Prosumers means who not only consumes, also produces. If I have rooftop solar on my roof in my building here, I am a prosumer because I'm buying power at night and then using my own power during the daytime. So this smart grid example I gave you here is more relevant to the prosumers because they can decide how much solar to use. Maybe they have excess solar at 3 o'clock in the afternoon. They may not use all the solar power themselves. They may want to use some solar power, store it, and use it in the evening when the demand is high, but no sunlight. Those decisions have to be made, and the data will come from this smart meter, smart automation system in the building to make it happen. The answer is yes. Thank you.
Okay, thank you, Mr. Ho. Is there any other participants who would like to ask questions? Yes, Mr. Ilwan, please proceed with your questions.
Assalamualaikum, Dr. So my name is Iroin. My question is, what is the efficiency of the smart grid technology in producing a greener environment?
Shaoxing, I could not follow that question. A lot of echo. Could you understand what he was saying?
Sorry, not really. Sorry, Mr. Ilwan, would you please repeat your questions or type it in the chat box?
Okay. So I repeat again. What is the efficiency of the smart grid technology in producing a greener environment?
This is breaking up.
Prof,
Can you type
Prof,
it?
let me repeat the question for you. He's asking what is the efficiency of the smart grid technology in producing a greener environment?
Smart grid is not efficient in the sense we talk efficiency. Efficiency is a very broadly defined term. You could say not efficient, effective is a better word to use, not efficient, effective. So efficiency depends input output. Yes, you are using electricity at different amounts, different times of the day. So you want to make sure you use less electricity during high demand period and more during off demand period, off peak period. So effectiveness is, can the smart grid do that for you? Answer is yes, because it can keep track of things changing and it can make adjustments, as I said before, in your domestic appliances to run them in a more effective way, giving you the lower cost supply of electricity. This is more effective. Thank you.
Okay, thank you, Mr. Ilwan. Is there any other participants who would like to ask questions? Yes, Mr. Muntasir.
Good evening, everyone. Good evening, Prof. I have just one question. We have the smart building now, and we have all the technology and each smart things. My question is the maintenance of this smart building, how I can conduct between the smart maintenance. Also, you get my question, Prof?
What do you mean by smart maintenance?
Yeah, because everything need now when we talk about the smart building, we use all the tools, the technology, the algorithm used during this building. So what about the maintenance? We can't just like advise or grade something or make modeling or connecting between the smart building and the maintenance. This is my question.
Yeah, maintenance comes in two ways. One is hardware, one is software. So as you can tell by now, I have to add new hardware in the building to monitor the temperature, humidity, noise, carbon dioxide, all that. That's true. New hardware I needed. I also need new software to run these systems. Maintenance is a good question. These hardware I've done that in many buildings in Virginia now. They're running for 4 or 5 years today, no problem. They have a limited life, of course. You have to be ready, replace them as needed. Of course, you have to be. Second is software maintenance. Like any other software, you have to maintain them to make sure if bugs come up, you can fix that. So there's a cost involved with that, you're right. but that cost is paid for by the improved building operation. You can run the same building using less electricity, less energy, and pay less at the end of the month because you are not using as much power during peak hours anymore. So yes, answer is you need maintenance, but this is standard practice of running any system that we are used to. Thank you.
Thank you, Prof. Thank you.
All right, thank you, Mr. Muntasir, for the questions. We shall take in the last question. Is there anyone who would like to? Yes, Mr. Cho Jun An.
I would like to ask Professor, in the current technology in Malaysia, how many years does this technology need to wait until it can apply in Malaysia?
I am sure I've seen in Thailand, Singapore, China, India, Bangladesh, these smart switches, smart plugs, smart controllers available in the open market. So if you can look around in Malaysia, I'm sure you can buy a smart switch, smart plug, and using those, you can do some initial example deployment of smart grid concept in your building. You can have that equipment appliance available in Malaysia, I'm pretty sure.
Okay, thank you, Mr. Cho, for the questions. Ladies and gentlemen, finally, we come to the end of the presentation. We would like to say thank you to the presenter, Professor Saifur Rahman, for the interesting presentation, and also to all of the audience for your active participation. Hopefully, the presentation will be beneficial for everyone. Before we end today's session, let us take a group photo. For those who are inconvenient, you may open your cam so that we can take a group photo together.
Okay, very good.
Is there anyone who would still like to turn on your camera for the photography session? If not, I shall proceed with the All right, I think that's all. I shall count down. Okay. 3, 2, 1, smile. All right, thank you so much. Ladies and gentlemen, you are welcome to scan the QR code on the screen, which will be posted later, or you can access to the feedback form through the link posted in meeting chat for the e-certificate. So you are reminded not to leave the meeting before you fill in the feedback form. Thank you for your attention. We hope to see you again in our next event.
Thank you. Bye-bye, everybody. Good evening.
Thank you, Prof.
Bye,
Bye-bye.
Prof. Thank you, Prof.
Good night.
Thank you very much, Prof. Bye.
Thank you, Prof.
Assalamualaikum.
Waalaikumsalam.
Mana scan-nya?
Dear participants, sorry to keep you for waiting. Please be patient and wait for the QR code. Dear participants, You'll be reminded to scan the QR code on the screen or access to the feedback form through the link posted in meeting chat for the e-certificate. Thank you. For those who have scanned the QR code and filled in the feedback form, you may leave the meeting. Thank you so much for joining us today. Dear participants, you will be reminded that the feedback form will be closing at 9 p.m. sharp. Please do fill in quickly. Thank you.
Thank you everyone for joining us. You may leave the meeting now. Thank you. Bye bye.